Hi, this is my final project presentation for CSCI E93. My CPU architecture is based on a MIPS-like language. It has 16-bit word size. It's word addressable. It has 16 registers. All the registers are general purpose except for register 0, which reads 0 and cannot be written to. Here's the block diagram for the architecture. It's very similar to the one that was provided in the notes during class lectures. I separated it out with layers and colors, which match closely to the stages in the CPU. So there's this stage where the PC gets incremented, and this stage where IR does a bunch of stuff, and stuff comes out of the registers. There's this stage where the ALU and the multiplier do all their thing, and the final stage where the results get written back and memory is accessed. So the instruction set for the MIPS-like language follows very much like MIPS. There's about 28 instructions and 4 pseudo instructions. The pseudo instructions are really there for convenience, right? For loading address immediates. Not all the instructions are used. So because this is a 16-bit instruction set rather than the 32-bit that MIPS has, it follows a different or a similar scheme. There's the class of R, I, J, and RR types, which I wrote specifically to get more instructions out of 16 bits. So for your R type, it's you do stuff with RS and RT and get back RD, and there's an opcode for that. Same with the I type and the J type, but for the RR type, the opcode is always 1111, and the function code distinguishes what's being done. So the disadvantage of this is that RS and RD will write back into RD. Yes. So the assembler writes code or takes in a file like this. It's MIPS-like in that it supports like an ASCII string data block and always requires a main function. So I did write an emulator in Python. There's a simple GUI in native TK, and it was very useful in debugging, and it's still useful in debugging. The special feature that I have is the hardware multiplier. It's used whenever you call these 3 instructions: the sign multiplication and the move from high and low. This is the first test for the software multiplier. We're going to use these numbers here, just one simple multiplication of a negative number and a positive number, minus 34 times 3. The result should be minus 102, which is represented as FF9A in 2's complement. Here I've got this switch here is for the clock divider so that we can see it when it starts to run. This switch here is for the memory suspend, so as soon as I flip that, it will start. These 4 switches here display register as LED lights, so we can take a look at that as it runs. So the first thing I will do is set it to 6, to 3, and then we can start it. So right now it's running. So we're back, and it looks like it finished with the FF9A value, and it did not take a short amount of time. So this time we're going to use the hardware multiplier. It's going to be the same values, the same clock divider, and you'll see the same result as well as in the same register. So run it, and let's see it on 3. So you still get the FF98 value, and it took a lot less longer.